Welcome to antenna as a component. In this video we'll discuss about radiation pattern. So what is a radiation pattern? It is a 2 or 3 dimensional plot that shows how the radiated field or power appear in the free space. Radiation wise, if we look to the electric field, we will find that it's some sort of magnitude divided by r, and there is some phase shift appear in exponential form, and then multiplied by what shapes it in the free space, some function of thetas and phi, and finally unit vector b, which represents the antenna polarization. If we plot this one in the 3 dimension, it will appear like this. We'll have some main loop where most of the power propagates. Then we will have some side loops which have some radiation, and in the back direction we'll have something called a back loop. Now we move to explain how the power propagate. The first one is the beam width, and now I'll plot some radiation pattern in two dimension. Assume this is what we have seen in the previous slide. Now as we see, there is some points which doesn't have any radiation, and this is what is called nulls. Null is simply a direction of zero radiation. So what is beam width between nulls? If we have two nulls, this angle between, assume this is theta 1 here and theta 2, this angle difference is the beam width between nulls. If this one was the main loop, then this is called main beam width between nulls. The second definition is half power beamwidth. Why this is important? Because we need to know how much most of the bar is focused. In this case also we look to the main loop. Assume this is this here is the peak, and this point and this point represent peak over 2. If this one is theta 1 and this one is theta 2, the difference between theta 1 and theta 2 is the half power beamwidth. So what is the types of radiation pattern? We have 3 types of radiation pattern: isotropic, omni-directional, and direction. The isotropic pattern means that the power is distributed equally in all directions. And if we look to the equation of the electric field, you will notice that the term which represents angles disappeared, means f of theta and phi is just equal to 1. If you look into dimension, you will just see a circle and with antenna at its center. Second type, which is omnidirectional pattern, is actually the closest form to the isotropic, because isotropic doesn't exist in nature, and it varies with either the angle theta or the angle phi. And if we look to the equation, we'll have function of theta or function of phi. And assuming we have a function of phi, how it will appear if we plot the 3 dimensional here, this x, y, and z, then if we look from up for xy plane like this, you don't have actually any theta here. You just have here phi, right? This means you will just see a circle. Another plane, if you are looking, for example, from this direction to the YZ plane, what you will see, you will do see some change with theta, right? If it is really a function with theta, something like this, for example. So depending on how you look to the radiation, you will see either a constant or just a variation, no variation with angle, or this, of course, this is theta is plotted with z here, so you will have a change with theta. Now we move to the third type, the directional pattern, and actually this is the general behavior of any radiation pattern, and the variation will be with angle theta and phi, and the equation will be maintained. So example, if you look either in xy plane or yz plane, you will do see some change, and you will see side loops, either of them. Of course, beam width will be different. Half power beam width between null may be different, but at the end you will see some variation in either theta and phi. Now we are with the takeaways from this video. We have learned what is a radiation pattern, which shows how the antenna radiate in two-dimensional or three-dimensional space. We have learned that we have three types: isotropic source, which is theoretical, and we have omnidirectional closest to the isotropic, uniform in one plane and varying with angle in another plane. And then the directional, which is the general one, and normally we expect that it will be stronger in some specific direction, producing high gain. We have learned that there is something called beamwidth, either beamwidth between nulls or half-power beamwidth, which quantifies how focused the radiation pattern is. And simply, radiation pattern analysis helps us to compare different antenna types and predict their performance. In the next video, we'll learn together how to plot radiation pattern. Stay tuned.